Hello once again, class, and welcome to another mock lecture. Coming to you live from my closet today because my girls are taking a bath. But this video is going to be about what do f prime and f double prime? What do the first derivative and second derivatives tell us about the original function, right? The base function. So we're going to start off with a table of things that we know. In the leftmost column, I have f. In the middle column, I have the first derivative, and in the last column, I have the second derivative. And here's some things that we know so far about the relationships between f and f prime. We know that when f prime is positive, then f is increasing. We also know that when f prime is negative, then f is decreasing. And my goal for today is going to be to fill this thing out. What are some other relationships that we can come up with? So far, to clearly state what we know is that if f prime of x is greater than 0 on an interval, then f is increasing on that interval. And then we could say the exact same thing for when f prime of x is less than 0 on an interval, then it's going to be decreasing on that interval. But is there anything else that we know from this? Well, consider this graph of f prime of x. And maybe what I want to do is I want to graph the original function. We've talked a lot about in previous videos that when f prime of x is equal to 0, that means something for f of x. It means that the slope of f of x is 0. The y value, the output of f prime of x, is 0 at those x-intercepts. And so it stands to reason that the slope of f of x, which is what the derivative is modeling, would also be 0, which means it's got a horizontal tangent line at those points. Well, when there's a horizontal tangent line, that correlates to when you have a local extrema. It's either a minimum or a maximum value. Okay, so here it is. Here is that particular base function. And notice that where you have a 0 for f prime, then you have a horizontal tangent line for f. And further, we can even deduce when our extrema is going to be a maximum versus a minimum, depending on how the derivative has its x-intercept. But first, let's clearly state this fact, right? If f prime of a is equal to 0, there exists, which is what this means, that little symbol right there, the backwards e, there exists, a local extrema at x is equal to a on the f of x function. So let's get that squared away. Local extrema for f means f prime has an x-intercept, and vice versa. Now in these graphs, in case you're curious, f of x is the base function is x minus 2 times arctan of x, and f prime of x is equal to x squared minus 1 divided by x squared plus 1. We would call f the antiderivative of f prime. We know that f prime is the derivative of f, but to go a step backwards, right, to come up with the function whose derivative we have, that would be finding the antiderivative. And it has a very simple definition. It says that an antiderivative is a function, capital F, whose derivative is lowercase f. So capital F prime is equal to f. So oftentimes you're going to be given a graph that's f of x, and it might say graph the antiderivative. And that's just another way of saying here's a derivative, graph the base function, right? Graph the original function. All right, so we have two graphs here. The first one, the blue line, is given to be f of x is equal to 1/2 x to the fourth plus 7/3 x cubed plus x squared minus 3x. The derivative, f prime, is equal to 2x cubed plus 7x squared plus 2x minus 3. And what I want to do is I want to try to figure out if we can determine, we already know that f has some kind of local extrema whenever there's an x-intercept for the derivative function. But is there a way for us to be able to tell when it's a maximum versus when it's a minimum in a local extrema sense? So let's try to figure that out, right? Can we tell when f has a minimum versus a maximum? The answer is yes, and it has to do with looking at what your derivative was doing before and after an x-intercept. If f prime of x is positive before the x-intercept and then negative after the x-intercept, then f of x has a local maximum. Okay, so here it is. It's before the x-intercept happens, then it's negative afterwards. That constitutes a maximum, a local maximum, right? That's why there's a local maximum right here. Okay, for a minimum, if f prime of x is negative before an x-intercept and then positive after, then f of x is going to have a local minimum. So in both of these cases, we have it's below the x-axis, the x-intercept happens for the derivative, then it's positive after the x-intercept. And so that's why we have local minimums for our base function, right, for f of x here. And so the answer is yes. That's why we say yes, we can know where it's going to be a maximum versus a minimum based on the behavior of the derivative itself. So we have these three things that we know about a derivative function and the antiderivative, or a function and its derivative. Namely, the function is increasing when your derivative is above the x-axis, it's decreasing when it's below the x-axis, and there's a local extrema when your derivative has an x-intercept. And we can actually say these same things about f prime to f double prime. So all the stuff that I just listed applies to f double prime and f prime, and that's because f double prime is the derivative of f prime. Okay, so here's what we had, and we can just say those same things about f prime to f double prime. So I basically copy pasted this section here, and I was like, well, look, that actually still applies right here, right? When f prime is increasing, f double prime has to be positive. When f prime is decreasing, f double prime is negative. Well, when there's a local extrema for f prime, that means there's an x-intercept for f double prime. And that's because f double prime, just like f prime, just like the derivative, models the slope of its antiderivative. That's what's happening. So it's modeling the slope of the model of the slope for the base function f. But there's got to be some stuff that we can know about f when we know f prime is positive and negative. So that's what I want to talk about next. Is there information we can learn about f from its second derivative? Okay, so here I went ahead and I graphed its second derivative. It's this green line here. It looks like this quadratic function, and that's because it is a quadratic. So from f, I want to look at how do we know, are there things we know about f looking at its second derivative, which is 6x squared plus 14x plus 2. And I want you to notice that when the second derivative, when f double prime is greater than 0, f of x is behaving in a very specific way, which means that kind of right here, trying to draw the straightest line I can, and it turned out absolutely terrible. But right here, where f double prime, I should say, is greater than 0, the behavior of this graph changes in some specific way, and the same can be said for when the second derivative is below the x-axis. So all of this stuff from here to here, right? X from here to here, the y values are below the x-axis. So the behavior, there is something different about the function in this region than in the whole rest of its domain. And that thing is called concavity. F is changing its concavity when its second derivative is equal to 0, when it has an x-intercept. So when it's above the x-axis, it has a specific concavity, and when it's below the x-axis, f has a specific concavity. And basically, to kind of, I'm not really going to define concavity explicitly. What I am going to do, though, is tell you that what we talk about when we say that something is concave up versus concave down is we're talking about where the graph sits in relation to its tangent lines. When a graph has concavity that's upwards, all of the tangent lines for the interval in which your function has concave up, all of its tangent lines are drawn kind of below the graph itself. That's concave up. Concave down is when all the tangent lines are drawn above the graph that you're looking at. So that's why in this region here, right, specifically this region, all the tangent lines for f are drawn above the graph of f, but everywhere else, all the tangent lines are going to be drawn below the graph of f. That's what concave down versus concave up is representing. So the things that we know are if the second derivative is greater than 0 on some interval, then f of x is concave up, meaning all of the tangent lines are going to be drawn below the graph of f. Think about it as the graph is sitting on top. That correlates to up. Whereas if the second derivative is less than 0 on some interval, then f of x is going to have concave downward behavior on that specific interval. It's interesting to note, by the way, that whether or not a graph is concave up versus concave down, it can still be increasing or decreasing on either of those situations, right? Like this entire graph is concave up. All the tangent lines can be drawn below the graph itself. And look, it's decreasing on a specific interval, and then it's increasing. Okay, here's an example of something that's concave down, where something that's concave down can still increase and also can decrease. So concavity is not really determining whether the graph is increasing or decreasing. That's the first derivative's job. But the second derivative is telling us what kind of curve is it? Is it bending upwards or is it bending downwards? That's the idea behind concavity. If f double prime, if the second derivative of some value is equal to 0, for some x is equal to a, then f has what we call an inflection point at a, and that is where the graph is going to be changing its concavity either from concave up to concave down or from concave down to concave up. So we wouldn't really be able to define the concavity at this point. That is the inflection. That's where it's changing its bend, if you will. So let's go ahead and add this to our table. So we know, we just figured out that when f double prime, when the second derivative is positive, that correlates to when you have concave up. When it's negative, that correlates to when the graph has, the original f function has concavity down. And when there's an x-intercept for the second derivative, that correlates to where you have an inflection point, where it's changing its concavity. And then we could, again, copy-paste this same sort of thing. You know, we don't really have, I didn't draw the third derivative on here, but you can imagine that if it's there, right, down here, you'd have, this is where it's positive, this is where it's negative, this is where there's an x-intercept. Right? And those things would apply to the second derivative. Okay, we don't get any information here. Like the fact that f is increasing or decreasing or has a local extrema, that is exclusively the job of the first derivative, but we do get the concavity information from the second derivative, and that's kind of really the point, right? If we want to graph an original function f, right, this is kind of what we're working with here. Now we're going to start doing a bit of graphing here in a second, based on some conditions that are given, or maybe based on a first derivative. But I wanted to mention something first, mostly because I just don't know where to say this otherwise. Consider these functions, all of which are the same basically up to this point. All I've changed is the constant that you're adding kind of at the end. P of x has a +1, h of x has a +7, q of x has a -12, and k of x has a +10,000. If I were to find the derivative for every single one of these functions, you'd actually find that they're all exactly the same. They all give you a derivative for 2x minus 3. So why is that an issue? Well, if I give us this graph and I say, hey, graph an antiderivative, there is kind of an infinite amount of stuff that we could graph. Any of these, for example, is a possible solution. So you have to think back on about what do constants mean in the sense of a polynomial like this. Well, it's changing where the verticality exists for the function itself. It's moving it up or down some specific amount. This is moving it significantly higher on the x-axis than, for example, p of x's constant does. But it would still constitute as an antiderivative. So oftentimes, if the book or somebody wants you to graph a specific antiderivative, it will typically say, oh, by the way, the antiderivative when evaluated at some value, let's say 0, is equal to 1. And that puts us in p of x is actually the only antiderivative that we could actually graph at that point. The only antiderivative in this scenario is just p. But if I get rid of that, then it's any of them. There's an infinite amount of things that we could choose from. Okay, so let's get to some examples.
Back to the lab again. Oh no, back to the lab again. We messed up. Back to the lab again.
All right, so example 1 says the graph of a guys, the music. Guys, listen, I know it's a banger, okay? But I got to get on with the math here. Thank you. So example 1, the graph of the function f is shown. Make a sketch of the antiderivative, which we're going to call capital F, given that capital F of 0 is going to be equal to 1. So this is a derivative, right? We need to come up with the antiderivative. Maybe you can think about it as the base function, or maybe this is the base function, and we're coming up with the antiderivative of it. Either way, this thing is the derivative of the thing that we want to graph. So there's a couple things that we need to look at here. First, I would ask myself, where is f increasing or decreasing? And I would actually make a note about this. Okay, I know that f is decreasing when the derivative is below the x-axis. So that's these regions here, right? That's why it's decreasing on that interval and also decreasing on this interval. And then it's only increasing on this interval because that's the only part of this derivative that's above the x-axis here. Second thing I do is I ask myself, well, where's the concavity changing? Now you have to imagine, well, what does the derivative of this thing look like? Because that's what's going to give us information about the concavity. So where this function, this blue line, is increasing, that's where our graph, that's where the derivative, you could say, is going to be above the x-axis, which in turn means that our antiderivative of this blue line will have concave up. Take a look at the table, right? This is the situation that we're in. We need to look at where f prime is increasing, which is, again, where f double prime is positive. that's a concave up situation, right? Where the graph is decreasing, that's where f double prime is negative, that's a concave down situation. Okay, so let's go back to here and take a look. Where's this graph increasing and where's it decreasing? And again, I made a note. I kind of separated my graph into these sections. Where the graph is increasing, that's going to be where my antiderivative is concave up. And where the graph is decreasing, that's going to be where my graph is concave down. The next thing to do is to actually mark some inflection points and some extrema. Now here, I am doing a little bit of guesswork, okay? Because I think that if you wanted to, you could put these really wherever you wanted to, as long as in relation to themselves, it makes sense. Now in my head, I'm kind of keeping this in the back of my mind, and actually we should probably just put that in. It's right here. The antiderivative when evaluated at 0 is going to give us 1. But yeah, these other points here, I kind of just marked in relation to the fact that I'm thinking ahead. I know that I'm supposed to have some concave down stuff, so it's not going to do this, right? That'd be concave up. It's going to have to do something like this. That's a terrible curve, but it's supposed to be bending down because it's concave down in that situation. So I will admit that this part, you're going to have to do some trial and error with to kind of sketch it to make it look like that it's satisfying the conditions that are presented from the derivative function that's graphed here. But this is what I came up with. Okay, so let's analyze it. There is an inflection point here. It's changing its concavity. There's another inflection point here, changing its concavity, and there's another inflection point here. It should be changing its concavity there. So it's starting concave down, then all the tangent lines sit below it, which means it's concave up. Then these tangent lines fit above the curve, so it's concave down again. And then at this point, the tangent lines are going to be fitting below, so concave up again. Okay, so the concavity checks out. What about increasing, decreasing? All right, well, the function's definitely decreasing up until we get to here. Then it starts increasing. Then there's another maximum right there, and then we're going to start decreasing again. But there is a decrease that changes its concavity. Still decreasing, right? Still kind of going down a little bit. I'm trying to draw a dotted line. It's not really working, but it's concave up and also decreasing. So yes, it seems to kind of check all the boxes that the first derivative function kind of laid out for us. And so that is indeed going to be the graph of the antiderivative. Example 2, graph a function that satisfies these conditions. Now I'm not going to read them all. I'll let you pause the video here if you want to look at them, see what our conditions are, see what we're working with. But the first thing I need is a graph. I'm trying to graph this stuff, so that's what I'm going to do first. Assuming that you pause the video and you're familiar with what's going on here, I don't want to take too much of your time with this one. The first thing that I'm going to do here is, just like in the last one, I'm going to set myself some intervals that are about increasing and decreasing, and then also about concavity. I need to get kind of the lay of the land a little bit. I need to know what the blueprint for my function is supposed to look like. So I'm going to first focus on items 3 and 4 on this list of conditions, and I'm going to partition up my graph, the plane, the Cartesian plane, based on these intervals. So negative infinity to negative 2, graph is supposed to be decreasing. Right? The derivative is less than 0, which means the graph needs to be decreasing. From negative 2 to 0, and also from 0 to 2, so kind of in both of these intervals, the graph is supposed to be increasing. That's interesting. And then the last interval that we have here is from 2 to infinity, the graph needs to be decreasing again. Okay, so that's increasing, decreasing stuff. Next, we need to tackle concavity. So again, I marked myself some intervals here, negative infinity to 0, and 3 to infinity. We've got a concave up situation, and the only time we have any concave down is between 0 and 3. The first two items on here help us figure out end behavior and kind of middle behavior. They're about asymptotes. The first one's telling us there's a vertical asymptote to the right at 1. So I guess you could argue maybe I didn't need to put the dotted line on this side, since this really only pertains to what's going on to the right here. But that's fine. I put it for the whole thing. My graph won't do anything special to the left, though. And then the second one tells us there's a vertical asymptote at 0. Now, notice that the behavior from the left and the behavior from the right don't agree, but that does tell us some stuff about what's going on at those points. So let's go back to where it's increasing and decreasing, because we know somewhere here there's going to be a local extrema, and somewhere here there's going to be a local extrema. That's where the graph changes from increasing to decreasing. nothing's happening at 0. 1, I guess because there's a vertical asymptote. But 2, the slope is still increasing in both situations, right? So we can't have, by definition, we can't have a local extrema there since it goes from increasing to increasing again. But here mainly it's mostly because of the vertical asymptote. So I'm going to put some points down. Again, these are kind of arbitrary. I just picked them. And in my head, I'm kind of thinking, oh, maybe it's going to do something like this. Because notice the graph needs to be decreasing first, then increasing, and that constitutes a local minimum. So some kind of situation like this is going to happen. And then here, this is going to constitute a maximum because it's increasing and then decreasing for that kind of collection of x intervals there. So in my head, I'm kind of piecing this together and I'm thinking maybe something like this is going to happen. Okay, we do need to assess the concavity. It looks like there's actually only going to be one inflection point, and it's going to be somewhere at x is equal to 3. Again, concavity can't really change here with an inflection point. It's going to actually change because of a vertical asymptote. So I'm not going to get to graph any point on this line since, again, vertical asymptote. But there is an inflection point somewhere at 3, and I decided to put it here. So that's where my graph is going to change its concavity. So now maybe something like this happens, where it's still decreasing, right? But now all of the tangent lines sit underneath it since we need to have a concave up situation. So at this point, I just gave it a sketch, right? This is kind of what I came up with. Everything, I think I check all the boxes. Let's check together. On the right, it's approaching 1. Okay, that looks good. In the middle, from the left, it's approaching positive infinity. Okay. And from the right, it's approaching negative infinity. So that checks out. The local extrema checks out. It's decreasing, then it's increasing, so local min. It's increasing, then it's decreasing, so local max. And that looks good. And then the last thing to kind of check is concavity. Is it concave up for the whole left side of the graph? And I would say, yeah. You can draw tangent lines that are all going to be underneath the curve. The curve fits on top of all the tangent lines. Is it only concave down from 0 to 3? It looks like it. All the tangent lines are going to be drawn above it, so the curve sits below, and then right here, it changes. And now all the tangent lines are going to be drawn below it, so the curve sits on top. So yeah, I think we've checked off everything. Everything looks pretty good, and that would be my graph. I will mention that, you know, this whole graph could have been down here, and it probably still would have been fine. You know, I could have done something like this. It's really hard to draw these things live. Oh my gosh. You know, something like that. And it still would have satisfied all the conditions. So we're definitely in a situation where there's going to be multiple solutions for this thing. Anyway, that is the end of the video. Hopefully you guys learned something. If you have any questions, please leave a comment below or send me an email. Thanks a ton for watching, and I'll see you in the next one.
Back to the lab again. Oh no, back to the lab.